welcome everybody. Today we're going to finish up our integration discussion, or introduction to integration and practicing with an important integration technique process that helps us kind of manage some of these integrals that we might not be able to find an exact antiderivative of using our typical rules. Okay, and so let's start to share the doccam and we can go through this process. All right. The substitution rule for integration. And when we start to go through this process more, you'll see it. We're going to be talking about U subs, right? U substitutions. Okay. And this allows us to integrate to find the antiderivative for functions, for expressions that maybe we wouldn't be able to directly use that power rule to directly find on that list of common antiderivatives, common derivatives to evaluate, right? And remember, we don't have a product rule for evaluating, okay, these antiderivatives. And so where some discussion comes in, this is a process to help integrate, help find that antiderivative, the composition of functions, right? When we have one function inside of the other. We had the chain rule for differentiation. Now we have this kind of substitution rule, the U subs, for integration when dealing with these compositional functions. And let's look at an example to kind of guide our work here. So for example, what if I wanted to evaluate, find this integral, this indefinite integral. But what if we have here 2x times the cosine of x squared minus 5 dx. And again, this is that 2x times the cosine of x squared minus 5x dx. Right, and so individually, we might be able to say, okay, well, I know what the antiderivative of 2x looks like. Do that kind of power rule, right? I know what that antiderivative of cosine should be, what function has the derivative equal to sine, right? But with that product, we want to be careful. We do not have a product rule, okay, for integrals, for integration. We cannot just multiply the antiderivatives of the separate functions. All right, we can't just break it apart. We can't separate it. These two have to work together in some way. Okay? And so when we look at that integral, I'm going to really reinforce that multiplication. Okay? Since we can't separate, what I want to hopefully, and whether it's an indefinite integral or a definite integral later, what I really want to emphasize, what I really want to kind of notice is the following. Notice that for this inner function, okay, we see that it's x squared minus 5 inside of the cosine, that the derivative of that inner function also appears, also shows up in our integral, in our integrand, right? That if I have that x squared minus 5, when I take the derivative, that's equal to 2x, right? Derivative of 5, the constant 0. So notice that 2x shows up in our expression as well, multiplying that function. And again, thinking about what I mentioned before, the composition, we took the derivative of composition of function inside a function. Remember our process, we take the derivative of the outer function, then we multiply by the derivative of the inner. That's exactly what we see here. So this substitution was going to help us manage these types of situations when we have that composition, when we see an inner function and its derivative all together as one product inside that integral. Okay, so let's see how this will work. Okay, so for our example, we had that 2x times the cosine of x squared minus 5 dx. We're going to create a new variable. A way of rewriting. Okay, let's let u be equal to that inner function. In that composition. Right? Then differentiate. Take the derivative. Right? So if I'm going to take the derivative with respect to x on both sides, what we're going to find is that this du dx, right, u prime, but I'll call it du dx, like our implicit differentiation before, right, df dx, dy dx, du dx is going to be equal to 2x, right? The 5 goes away, power rule. And what we're going to see here, we can multiply both sides by this dx. Those differentials, these little components, because they are separable, we can multiply them like they're variables. So that way du is equal to 2x times dx. So now we have these following statements, that u is x squared minus 5, du is 2x dx. We have created these new statements. So then in our integral, reinforcing that multiplication again, and even that dx is like a multiplication, right? That height times the width, right? And so there's no harm in rearranging a little bit. If I take this piece and I slide it after that cosine, this is the same thing as having the cosine of x squared minus 5 times that 2x dx, or 2x times dx, okay? So I just rearrange, right, that commutative property for multiplication with these different factors. But then when I start to rewrite, notice that that x squared minus 5, that was just u. This 2x dx is just exactly du. So now with that rewriting, replacing, substituting that longer expression, that inner function with this u, symbol, that derivative du, apparent, visible in our expression as well. Now we have an easier, a more direct integral with only u's, right? U and du. And this cosine, just like we had a theta and x, the antiderivative of that cosine is the sine of u. And since we have this indefinite integral, don't forget the plus c. That antiderivative, their sine, but we want it back in terms of x. We want that final answer in terms of x, our original variable. So that way we get here the sine of what was u. U was equal to x squared minus 5. And then our plus c, our constant of integration, still present. So we can see that relationship that we have in our function and its derivative multiplying present as parts of my original function, my original integral, we can rewrite in terms of that simple u variable or u sub here. And I hope that antiderivative is easier to manage, is easier to deal with. Okay? But it's just a matter of ensuring that we can see those components. Okay? All right. So let's check out another example here to see how this will work, and looking at a problem with limits of integration at definite interval. Okay? And so let me make this note up here. Important note for definite integrals. I make this big point because it helps us in future courses if we make a substitution for the variable, right? That is, if we're doing a u sub, that we change our variable that we see present in our integral, we must also change the limits of integration. They have to match, they have to go along with a new variable, okay? It's something that lazily some students may skip and go back to their variable, but it's going to alleviate some work later. Okay, so I'm trying to incorporate it early so we get used to doing this process. Okay, it's just beneficial. Not necessarily say it's lazy, but it's just definitely cuts down a lot of extra work and thinking in the future. Okay, so let's look at this next example. I'm going to borrow this one from the textbook. Let's check out this one. Kind of interesting as well. Let's try problem number 63 on page 419. Okay, and we're going to integrate from 0 to 13. This integral dx over the cube root of 1 plus 2x, that quantity squared. Okay, and so looking at that integral, some notation changes here. just to start to sort and organize. Well, one thing, right, having that dx in the numerator is fine, but this is the same thing as if I put a 1 there for my placeholder in the numerator, 1, the dx I'll slide off to the side. And we saw that cube root of 1 plus 2x squared, or one more statement on this line, that cube root of 1 plus 2x squared, power root, the index of a radical, I can make this 1 plus 2x, power over the root 2 thirds. Okay? But I can't distribute that 2 thirds in. I can't separate that addition. So in this case, this is not a direct antiderivative we can find. It's not a simple power rule. It's not one of those ones on our list. So let's start to look at these expressions, right? Well, definitely we have something going on inside of that's cube root. So already there, I start to see this composition, right? We have this 1 plus 2x squared inside of that cube root. So that starts to get me thinking a composition. Right? And so when we have this 1 plus 2x raised to 2 thirds power, right? Then I start to see, okay, well, my inner function my u 1 plus 2x, taking the derivative on both sides, of just that inner function, right? The powers, the squaring, the cube root, I've kind of built in as this rational exponent, right? So I'm just taking the kind of focal innermost function, 1 plus 2x. That addition include 1 plus, okay? Because once I take that derivative, du dx, derivative of 1, 0, derivative of 2x is 2, multiplying both sides, the dx, du is equal to 2 dx, right? I'm going to do one more step here, but looking at that original integral, right? Here, that's our u. Here we have 1 dx, but over here I have 2 dx, right? So if I focus on that dx part, if I divide both sides by 2, this means 1/2 du is that dx, right? So I can see this dx I can replace with a 1/2 du. I can take that expression as a whole to replace the dx. And so in some of these cases, that's what some instructors, some text online work does. They do the derivative and they isolate the dx part instead, multiply over, divide out what we need to do, and they use the dx and replace that entire expression and try to simplify down there. But for me, sometimes that includes it has variables, x's and u's working together, which cancel, but this is a little bit too messy for my taste. So this is why I do it this way. I try to kind of match up to what I see in terms of just u's, maybe a constant, a coefficient, but it gets those pieces kind of nicely condensed down. So we start to see where these components are going to be replaced. But now, before I forget, we're going to need our new limits. Okay, so our lower and upper limits, those corresponded to the x, right? So when x was equal to 0, our u, 1 plus 2x, right? 1 plus 2 times 0 becomes 1. So that's our new lower limit. For my upper limit, when x is equal to 13, u, 1 plus 2 times 13, 2 times 13 is 26 plus 1, 27. There's our new upper limit. So when I change my variable to u's now, du, these limits need to correspond to what's happening to u. Okay, so let's put this all on one page. I know it's a little messy here, but hopefully looking back on these notes later, it'll be able to follow. Okay, so in our problem, that integral from 0 to 13, 1 over 1 plus 2x raised to the 3, or the 2/3 probably power, 2/3 power dx. This becomes this integral 1 over u to the 2/3 power. And then that dx became 1/2 du, right? And then our new limits, they went from 1 to 27. Okay, lower 1, upper 27, replacing 1 plus 2x with du, the dx 1/2 du. So now it's only u's appearing, and then my new limits. And so some notation here, that 1/2, I'm gonna bring outside one of the properties of integrals I may have forgot to mention, just like derivatives, coefficients constant, we can bring outside that integral. It's not going to change. My founders always have to remember to multiply with it. My limits of integration, 1 to 27. That u to the 2/3 power in denominator, u to the negative 2/3 power. And we still have that du inside. Right, so that 1/2, that coefficient, right out front. U 2/3 in denominator, bring it up to numerator, the negative exponent, still my new limits there. And so as I start to evaluate, that 1/2 stays with us. Finding the antiderivative u to the 2/3, negative 2/3 plus 1, negative 2/3 plus 3/3 is 1/3, positive. So I get u to the 1/3 power, that cube root. My limits of integration, 27 to 1. I don't need the constant integration, I need that plus c here because I have values I'm going to be plugging in at the end. So I do that calculation, I get a solid number result. The constant integration not necessary. That's only for indefinite integrals when we're trying to find that most general antiderivative for our solution. All right, and so then just one more line here. That u to the 1/3, that's the same thing as having the cube root of u. And we're going to evaluate 27 and 1. I'll make a side note of this later, but just finishing this up, right? Now that I've changed my limits of integration, it makes the calculation that much quicker because now I'm just going to take the cube root of 27. And remember, it's always a subtraction. The upper limit, take away the lower limit, the cube root of 1. That 1/2, that coefficient following us, you can distribute it in if you want to. The cube root of 27, 3, cube root of 1, 1, 1/2 times 2, or just simply 1. There's our final answer. Okay. And by changing the limits of integration, it makes hopefully these calculations a little bit more straightforward. But one thing we can mention, at this stage, if you wanted to, we can substitute back to our original variable and limits of integration. So as a side, we could have also done 1/2 this cube root. And then what was our u? 1 plus 2x. And using our limits of integration, going back to it, 13 and 0. And then once you compute, you should still end up with the same result of 1. All right. So as long as we can see the relationship of the derivative of the inner function appearing in that same expression, probably a little bit more apparent with our cosine problem earlier, the inner function and its derivative showing up, and it should be a multiplication, not adding together, multiplication together. We can do this substitution rule, this U sub process for evaluating those integrals. Okay? All right. If you have questions, let me know. Otherwise, there we are. The end of our integration introduction discussion for our first semester calculus course.